Start, sir. Okay, sir.
I think everyone is audible with my voice. I think so.
Yes, sir.
Yes. So, like last day, I was having some disturbances and technical issues, and now I continue the slides which I have not finished. So, like the main process, two processes are subtractive and additive manufacturing in manufacturing processes. Like you all know, I just briefed regarding subtractive manufacturing and additive manufacturing. The major difference is like that, like in subtractive manufacturing, the material is obtained by continuous or subtractive process, continuous removal of material from a billet or a block. But in additive manufacturing, as you all know, it is the final object is obtained by adding up of layers. So can you go to the next slides, Joseph? I have completed all this. Next. Yes. So like we were in this slide, like what is power of digital manufacturing? So actually 3D printing is and additive manufacturing is a digital manufacturing process. So like as you get a survey from a manufacturer or a manufacturing company, like 3 in 1 believes that 3D printing will become as more important than traditional manufacturing, because traditional manufacturing have a lot of limitations, but in additive manufacturing most of the limitation can be overcome comparing to a traditional manufacturing or conventional processes, like the material infill control or the processing of complex shapes, the material variability. All this limits in traditional manufacturing process, but we have a good good features and good advantages in additive manufacturing compared to traditional manufacturing, conventional manufacturing processes. 11% of manufacturers believes that 3D printing is ready to produce end-use product. That means functional products. And most agrees that 3D printing represent as more sustainable than conventional process, because it is a sustainable concept. The 3D printing or additive manufacturing is having a sustainable concept. It also uses raw materials which is very compatible, biocompatible and biodegradable materials also. So it is very sustainable to nature as well as the processing technologies. Then the main three advantages of additive manufacturing are like its degree freedom of design, then customization, mass customization. We can do the mass customization through 3D printing technology. And 3D printing technology take your idea or thoughts very faster to the market. You can reach the consumers or customers very faster manner, fasting up your research and development, R&D of your product, your thought. Next slide. So as you all know, what is 3D printing? It is like, next slide. Next slide. Next. So this is actually the process involved in 3D printing technology, additive manufacturing. So any processes, like any technologies, you can classify 3D printing technology into different categories based on its processing technology. So, but the process flow is same for all technologies. Like you will be having an idea. The first stage of the process, 3D printing process is ideation or ideation of your problem, or like creating an idea. It is the first stage of 3D printing. Next, you have to take that problem into a conceptual design or into a model. So for that, you can use CAD modeling softwares, or you can go with scanning process. And by this process, you get a output as a 3D model. And this 3D model is then again transferred to a slicing software, A slicing software slices that model into n number of layers, and it also converts that layer into machine language. This machine language is nothing but it's G code and M codes. And this G codes and M codes machine language is transferred to or uploaded to a 3D printer. Before on uploading, simultaneously we upload its raw material. If you go with FDM printers, FDM fused deposition modeling, or FFF printers, we use spools or filament kind of raw material. If you go with SLA technology, stereolithography apparatus, we uses resin kind of material, liquid based raw material. If you go with SLS, we use powder kind of raw materials. So based on the technology you are choosing, you upload, feed the raw material to the machine. Then the machine, according to the G code and M codes, the machine language which is generated from a slicer, it operates and we get the final object what we require. So it is 3D printed by the process of additive manufacturing, laying one over the other. The material is laid one over the other, and we get the final output. So this 3D printed part is then taken for post-processing based on our requirement, that based on its functionality or aesthetics or testing factors, we post-process it. So there are a lot of processing techniques. So based on our requirement, we post-process it. So this is the basic flow diagram for every 3D printing technology. But in terms of its technology, we feed the raw materials based on it. So if it is an FDM, we uses solid kind of raw material. If it is an SLA, we uses a resin kind of raw material. That means liquid state. And if it is in a power SLS technology, we uses powder. Then DLMS, we uses metal powders. So similar manner, only the raw material and the processing techniques differ, but the flow is same. Next slide. Next. So you can come to next slide. Next slide. Next slide. Next. Next. Yes. So the basic 3D printing technologies we can classify into four actually. The first one is SLA. SLA means stereolithography apparatus. It is the first of kind discovered by Charles Hull, and he used a photoresins which cures on passing a laser over it. So like here there will be a tank, resin tank. So there will be a plate, and when laser source will be there. When laser source passes through its resin, that resin in the tank, it solidifies. Where it touches the laser, where it touches the resin, it solidifies and it builds the object on the build plate. So here we normally uses photoresins based on its intensity of curing. We uses laser sources. And there are a lot of categories of its raw materials itself. Like we can use castable resins, then wax kind of resins are there, dental resins are there, flexible hard resins are there. There are a lot of variants for the SLA resins. And the benefit of this machine is like we will get a good surface finish, as well as we can opt for higher layer resolution in SLA technology. Then next one is FDM, fused deposition modeling, or we call it as FFF technology, fused filament fabrication technology, and it is right now used for every commercial purpose. And it is a very basic concept in 3D printing, and normally we uses this technology for testing as well as for the functional prototyping. So here in FDM printers, there will be a spool of raw material. We also call it as filament. It will be in a solid wire form, and this is fed into a head where a cartridge and a nozzle is attached. when this cartridge get heated, it transfers the heat form to the nozzle, and this filament which flows through the nozzle get into a semi-molten state. And this semi-molten state of material is deposited one over the other based on the G codes and M code we generated through a slicer. And we get the final output what we designed through FDM printer. So here the raw material which we used is a solid state of wire form, and we get the output as what we require in a designed manner. And in FDM printers, we uses thermoplastic material. We only uses thermoplastic material such as PLA, polylactic acid, ABS, HIPS, then PC material, polycarbonate material, all which all differ in their strength, in their property, and there are a lot of variants of material available for FDM also. So next one is DLMS, direct metal laser sintering technology, and here we uses metal powders, and high-end lasers are equipped to cure these metal powders. So this is similar to SLS technology. The concept is similar to SLS technology, but the raw material which we are using here in this technology is metal powders. So when this high-end laser passes through this metal powder, where the laser comes in contact with the powder, it solidifies. The rest it is powder as it is. So here the benefit of this, like, we does not require a support material or a support structures compared to FDM or SLA technology in DLMS, since it is already printing in powder base. And the next one is SLS technology. So here in SLS technology, we use a thermoplastic material, and it also cures with a laser. When when laser passes over the powder, plastic powder or thermoplastic material, it solidifies. So these are the major, or the four types of categories of 3D printing basically available in market. Next slide. So these four technologies are advanced 3D printing concepts. They are used for bioprinting, printing in architecture or construction segment, then PCB modeling, then food industries, food processing. So as you all know, bioprinting concept means like printing of organic tissues or cell. It is called bioprinting. So in this, bio inks are used to print the shapes or required organs. Then in construction, right now in Japan and China, they are using 3D printers for construction of houses, buildings, and even hospitals. Like you may read through many newspaper contents constructing houses through 3D printing. So it is like a what you say, it is very good advancement in construction or building segment. So it fasters the construction, and also we get a good output, good strength building through this method. So it is completely operated, computer operated, so no manual interference is there. So we can utilize the total machine through overall the projects. So then PCB construction is very intrinsic, and PCB modeling or making of PCBs is very intrinsic and a complicated process, and it can be done through 3D printing process. Then food industries, there are a lot of food 3D printers. You can print desserts, your food items, or many, even you can go with your controlled diet food items. Like if you are diabetic patient, you can control your insulin content in your food through 3D printing. If you are a BP patient, you can control your intake of salt or some other composition through printing your food items through 3D printing. So next slide. So like now I need to go with slicing and slicer softwares, but like instead of my theoretical explanation, my colleague and my partner, Mr. Joseph, will demonstrate how you can slice an object through using slicers, and how you can transfer this sliced object to a 3D printer, and what all parameters you can make, like you can do or change while you print, and what are the its output. So he will give you a direct demonstration as well as a theoretical explanation comparison of this slicing process and different slices, regarding different slices, and also its output comparisons. So how it changes if we varies its temperature, how it affects the output and strength, output in regards of strength, in regards of finish. All these things will be briefed by Mr. Joseph, and I hand over the session to him. And again, I apologize regarding my session. I could not complete my session properly because there were many issues, like technical as well as many. I don't know what happened, like even network issue. Maybe it may be due to network issue or some problems, my device problem or something like that. I apologize for this the problem it caused during the session. So, like I hand over my session to Mr. Joseph. He will continue the session with this points. Thank you. Thank you very much. Thank you to all.
Thank you, sir. Thank you, sir.
Thank you, Bashir.
Thank you, Bashir, sir. Thank you, sir.
Thank you.
Sir, Joseph, sir.
Yes, sir. Yes, sir.
Ah.
So I will start, sir.
Okay. I'll to present this your PPT, sir.
Okay, I will share, or you will be loading, sir.
You will share, sir. You will share.
Okay, fine. So let me know if any disconnection or anything, sir. Yeah.
What happened, sir?
No, sir. If the line gets disconnected, just let me know, sir. Yeah, no, I am not getting the share screen option, sir.
Wait, sir.
Yeah.
Hello, the file is converting, sir. So please wait for 2 minutes, sir. 2 minutes, sir. Okay, sir. Okay, sir.
Yes, sir.
Yes, sir. I introduce you, sir. I welcome our Joseph, sir. He is one of the managing director in the Insta 3D printing. Now he is going to take the topic on virtual demo on slicing software. Sir, welcome you, sir.
Yes, sir. Yes. Thank you, sir. Thank you. So, good afternoon, everyone. A warm welcome to all. It's my pleasure speaking to you in this session. This session, I'm going to speak about how a slicing software works, and preferably we are going to look at more deep into the FDM process of 3D printing technology. So, thank you, Hindustan College of Engineering and Technology, Department of Mechanical Engineering, for arranging this online FTP program supported by AICTE Atal Academy. So So we will be starting the session now. Yeah. Next slide. So as you know, there are two types of manufacturing process. One is additive and the other one is subtractive. Next. Can I get the control, sir? Can I change the slide so it will be easy for me? Is it possible?
Yes, sir. Yes, sir.
Yeah.
Right.
So subtractive manufacturing. So this
You
subtractive.
can change, sir. You can
Yes,
change.
sir. Yes, sir. Yeah. Thank you, sir.
Thanks, sir.
So this subtractive manufacturing method, it's of many different types like turning, milling, drilling, EDM, grinding, CNC machines. Everything is comes under subtractive manufacturing method, where a raw material is converted into a product by removal of material, and it involves loss of material and wastage of material. Whereas in additive manufacturing method, it's totally different, where the waste removal is very minimal in additive manufacturing method. So there are more advantages when compared to the conventional subtractive manufacturing method. So there are few process parameters which influence in subtractive manufacturing method. These are the process parameters involved in subtractive manufacturing. Preferably in all the process, there will be feed, speed, tool orientation, cut direction, coolant, depth of cut, tool geometry, etc. So in additive manufacturing, so before going deep into the additive manufacturing method, let's see what is additive manufacturing. So this refers to a process by which a design data obtained from a CAD model, CAD software, is used to build up a component, is used to produce a component or produce a product, end product, by depositing layer by layer over one another. So hence the final product is received from the 3D printer or additive manufacturing machine. So this is the main difference between conventional subtractive manufacturing process and additive manufacturing process. Here the scrap or waste is very high, but in case of additive manufacturing process, the scrap or waste is very, very less. So in technical terms, 3D printing is also called rapid prototyping, which is the automatic construction of physical objects using additive manufacturing technology. So material is getting added layer by layer in order to get the final component. That's the basic principle of rapid prototyping or additive manufacturing method. So these are the other terms which is used to represent what is rapid prototyping and everything. So solid freeform fabrication, automated freeform fabrication. These are the other terms which is involved in representing 3D printing or rapid prototyping technique. So there are many types of 3D printing techniques. Hope you have a good knowledge on the different 3D printing technologies. I'm not going deep into the 3D printing technologies available, but I will be speaking about the characteristics of 3D printing technologies which are available. So these characteristics involves various process parameters or various capabilities or versatility of the technology to give us different 3D printing experience. So the types of 3D printing, it differs based on different building mechanism, different price points, different materials, and different applications where it is used. So hope you can see it. So these are the different 3D printing technologies available. First one is FDM, SLA DLP, SLS, material DOD, and binder jetting, and DMLS, metal printing section. So these are the various 3D printing technologies which is available. So let's see it one by one. The characteristics, let's see it one by one. So as you know, FDM is a technique where solid material in the filament form is inputted into the extrusion head, where it is getting into the molten state, and it is being laid layer by layer onto the build platform. So the final product is obtained. So this dark blue color is the real build material, which is the part or component which is being printed, and the light blue color is the support material which supports the overhanging structures so as not to disintegrate into the platform. So these support structures are of two types basically. One is breakaway support structures, and the other one is water soluble support structures. So this depends on the type of machine which we are using. So mostly all will be using breakaway support structures. So this is the FTM technology. And regarding the characteristics of FTM, there are various process parameters which we will be discussing in the slicing software. These are some of the main process parameters. One is the layer height, infill ratio, shells, and infill pattern. So I will be explaining deeply or briefly in the slicing software section. So these are the basic parameters where we can change the process parameters as per the requirement or as per the application of the 3D printing which we are into. So these are the process parameters, and the errors which is happening in FTM technology are like two types. Warping effect is there, and this or proper layer adhesion is not happening in the 3D printed model. So what is a warping effect? This warping effect is called like the adhesion between the build platform and the first layer. If it's not good, the material tends to bend upward. So if this is a 3D printed component, and if warping occurs, it will bend upwards, so that the 3D printed corners or the edges will be slightly warped, and this is due to inconsistent extrusion or inconsistent cooling down of material. So if you are building a big component, say we are printing about a 500 mm by 500 mm component, which is around half a meter. So when printing a bigger component, this cooling, the material needs to cool instantly once the material is getting laid. So the 3D printer head moves from here to the end of the 3D printer, and in order to finish the first layer, it will take about it will take about 4 hours to finish the first layer. So in that 4 hours, the cooling of material will be like partially inconsistent, like it will not be perfect, and the environmental condition surrounding the 3D printer also influence the warping effect. If it's too cold, it starts to warp easily. If it's hot, warping effect will be minimal. So only closed enclosure 3D printers get less warping effect. And similarly, since warping occurs in the bottom side of the 3D print, heated bed is used in a 3D printer. So heated bed maintains the temperature of the 3D printed part, getting stuck to the 3D printed bed. So next is the layer adhesion. So as you know, the filament is melted in the 3D printing extrusion nozzle, and as it flows out of the 3D printer extrusion nozzle, it gets laid onto the 3D printing hotbed or the 3D printing platform. So in this case, if the 3D printer nozzle is around 0.4 mm in diameter, if the size of the nozzle, 3D printing nozzle is 0.4 mm in diameter, the output of material which is coming out of it will be mostly around 0.39 to 0.42 mm in diameter. So this material, when getting deposited, and if you are giving a layer height of 0.3 mm, so there will be a 0.1 mm layer adhesion between the layers, so that increasing the layer height, which means if we are using a 0.4 mm nozzle, if we give 0.3 mm as layer height, or if you are giving 0.2 mm layer height, or decreasing the layer, like it's called the layer resolution. By increasing the layer resolution, you can obtain a stronger part. So the layer adhesion between layers will be very high. So in some cases, when printing some difficult materials such as ABS carbon fiber or nylon PC, there are possibilities of layer adhesion problems happening in a 3D print. So this layer adhesion problems can be controlled based on the parameters which we are providing, or the environmental conditions where the 3D printer is kept in. So next one is the SLA or DLP method. SLA is something like it uses laser as its light source, and DLP uses projector as its light source. So as you see, this in SLA technique, there will be a laser pointing at the 3D printing platform, and this is the resin material. Both uses resin as the raw material. It's in liquid form. So when the light focuses on the resin, it is photosensitive in nature, so it gets cured right away when the light is falling on the resin. So in SLA, the laser point focuses onto the resin, and in DLP, at a time, the whole first layer or the second layer is being focused by the, or it is focused by the DLP projector. So in SLA, some time in regarding the comparing with the time taken between SLA and DLP printer, SLA is a bit slow, and it depends on the machine which is used. If in higher industrial grade machines, it's obviously fast, and in normal basic machines, commercial basic machines, when comparing DLP with SLA, the curing time is bit faster in DLP method, whereas the finish and other things are very much good in SLA technique. So this is the basic difference between SLA and DLP method. There is another type of 3D printer in SLA, which is called the SLA LCD 3D printer, which is the new version of it. In this, LCD screen is placed and a UV LED light is being passed through, and the even you can use your phone to 3D print nowadays. There are many 3D printers, small 3D printers, which is available in the market, where we can just keep the platform or resin tank over your smartphone and then start 3D print. So this is how a 3D printer, SLA LCD or SLA 3D printed part looks like. These are the support structures, which is called tree type support structures, which can be cut using the pliers. And this 3D printed part is very smooth, and it has a good surface finish. You can also use it for mock models, or you can directly use it for end products where the resin used is tough resin, so it can handle higher temperatures, and it has a good strength as well. So in case of characteristics of SLA 3D printer, mostly all the printer parameters are being fixed by the manufacturer. Only the layer height and the support details or the build size varies, and which can be provided by the 3D printing users. And similar to FDM warping effect, there is an effect called curling, which is happening in SLA technique. You can ask, why does a SLA 3D printed part curls or warps? In FDM, there is uneven cooling temperature, but whereas in SLA, it's normally a laser which is focusing the resin. It's simple, and it just a photo reaction is being taking place to cure. So in this case, how a curling occurs? So once the first layer is focused using a laser or a DLP projector, the first layer cures and it sticks to the build platform, and then the second layer cures. So this second layer, when getting cured, pulls the first layer so that the ends get curled or warped away. So in order to reduce the warping effect, we will be placing the 3D printed component in a 45-degree angle so that this warping effect can be reduced. And the layer adhesion is very high in case of SLA 3D printer when comparing with the FDM 3D printing technology. So this is the SLS technology, where we use powder and a laser as its heating element. So this laser heats or melts the plastic powder, thermoplastic powder. Basically, they use nylon ABS powder. Even certain other powders are also used in the SLS technique, where this laser melts the powder and combines or joins the powders into a cross section as per the requirement of the part. So in this case, the supports are not required. The part support structure, the powder acts as a self support, so that there is no problem in the overhangs. So as I said, the characteristics is like no support structure is required. Layer height can be adjusted by the user. Layer addition is bit minimal when compared to SLA technique. It's because of the porous nature of the 3D printed component. Since we use powders, the powders when sticking, there will be a small gap in between the molecules of powders. So the porous nature makes it to look a bit rough or matte finished. So we can just dye it, or we can use any other post-processing technique in order to improve the quality of the 3D printed component. So here also there is a problem called a shrinkage and warping effect, and it's similar to the things which was discussed in FDM and SLA techniques. And there is a case of over-sintering which is happening in SLS technology. This over-sintering is like high heating of raw material. So once the laser is focused onto a raw material, if we have say 1 mm wall thickness and there is a 1 mm dia hole in the cross section of 1 mm. So the 1 mm hole gets over sintered and there will be no hole visible when we get the 3D printed output. It is because of over sintering. So we need to increase the wall thickness, or we need to control the laser parameters accordingly so that you can get a full good 3D printed component out of the 3D print, SLS 3D printer. And in case of SLS 3D printed part, the whole, if we are printing something like this, and it has a hole inside, or we are printing a globe, a hollow globe, hollow sphere, where we have a hole inside. So the empty space gets filled with raw material, plastic, nylon, or any raw material. This raw material needs to be taken out, and we will be providing sink holes in the 3D printing design. So when designing a sphere, there will be a hole given below so that the extra material which is trapped inside the 3D printed component can be released easily through the sink holes. So next is the material jetting technique. Here a nozzle is used. It is similar to a printer which is normal 2D printer. Here nozzle supplies the material and a UV light cures the raw material which is laid onto the platform. So there is a nozzle which is supplying, as you see, there is a, sorry, yeah. There is a nozzle supplying the raw material and the support material as well. And there is a UV light which is behind the nozzle, so that as the nozzle supplies the raw material, this UV cures the raw material so that a layer adhesion happens and the final product is formed. So when speaking about the characteristics of material jetting technique, it can handle almost multiple materials. So the most favorite material jetting technology used is the PolyJet technology of Stratasys, where multiple materials can be used. I will say example, the materials used in PolyJet technique is of two types. One is the Vero material and other one is the Tango material. Vero is slightly hard in nature and the Tango is elastic, flexible in nature. So combining these two proportions, like if you are using 100% Vero material, the total component will be very hard. You can even change the shore hardness values of the material, so that by inputting the shore hardness value, the slicing software itself automatically balances the amount of material of Vero and Tango. If we need a slightly flexible part, we'll be reducing the Vero material and increase the Tango material so that you can get a flexible part. Even a single part which has both flexible as well as soft as well as hard material can be printed using a PolyJet technology. So in this you can see it's a 3D printed remote where the white color is the hard material, Vero material, and the black one is the Tango material. The black one is a bit soft and the white one is hard in nature. So even you can vary the shore hardness values using this technique. So even full color printing is possible using this technique. Since it's nozzle type 3D printer, there will be multiple nozzle heads, so around 1000 nozzle heads in a PolyJet 3D printer. So easily you can attain full color 3D printing. Any color is possible using the 3D printing technique. So it's depending on the machine, it varies. So there is also a dissolvable material available in order to dissolve the raw materials, or using high jet water or air compressor, you can just remove the supporting material which is available. Just a second. So the layer height which is possible in this PolyJet technology is very minimal as possible. Like 16 microns can also be achieved using a PolyJet 3D printer, which is very rarely seen in other 3D printers, which is a good layer height. You can get a good output out of this 3D printer, material jetting 3D printer. So there are two types of finish which is available in this material jetting technique. One is the glossy finish and the other one is the matte finish. So as you see, the glossy finish is very shiny in nature, but the matte finish is a bit rough in nature. So in this, in glossy finish, the supports are meant to be there where the support is required. So in matte finish, the support will be engulfing the overall part. So the matte finish is the output. So in glossy finish, only where support is required, there the support occurs. In matte finish, the total part is, in spite of any orientation or any overhanging angle, the total part is engulfed in the support structures. So the finish differs when we give it as matte or glossy. It is available in the software whether we should go for matte or glossy finishes. So next is the binder jetting technique. This is something similar to the SLS technique, where here also it uses powder. The feeder rolls the powder onto the platform, and the binder or any binder can be used in the nozzle in order to combine the powder. So binder jetting technique is a popular technique where large 3D prints can be formed easily. Something like sand casting cores and molds can be produced using a binder jetting technique. Full color printing is possible using binder jetting because when supplying the binder, you can also add color to it, and there is no support required as it uses powder. So it acts as a self support, and the layer height and adhesion is bit the mechanical properties is bit low in case of binder jetting technologies. So we go for post-processing techniques like infiltration and sintering. So we infiltrate it with other metallic components. Brass can be infiltrated into it. So the part gets mechanically stable, and even you can sinter it for a long time so that you can get a good hard 3D printed plastic out of it. So the metal, instead of going for a metal printer, there are printers available in binder jetting using metal raw material. So in this case, you can just get a component at a very fraction cost of a metal printer. So metal printing is also possible in binder jetting technology, but the mechanical characteristics will be very low when compared to other processes. So this is metal printing, and it is highly recyclable. It has good dimensional accuracy. Layer height can be varied. Hollow sections and lightweight structures can also be produced using metal printing. Only that we need to post-process it after 3D printing so that you get a good surface finished metal printed component. So we have seen what are the characteristics of different 3D printing technologies. Hope you got a glimpse of every technology which is used and its few characteristics of the 3D printing technologies. Now, let's move into the slicing software of FDM and FFF technology. FDM is called Fused Deposition Modeling. The other commercial name is called FFF, Fused Filament Fabrication. Fused filament fabrication, FFF. So what are the filaments currently under research? There are many 3D printing filament, thermoplastic filaments available in the market, which is called PLA, ABS, ABS carbon fiber, PLA carbon fiber, PETG, ASA, which is acrylic material, nylon PC, and other alter materials. Everything is available in the market. So there are a few 3D printing filaments which is coming into the market, which is a blend of these 3D filament materials. So there are also metal filaments which is available in the market right now. Stainless steel along with PLA material is being mixed and provided as the raw material. So we can just print stainless steel using a FDM 3D printer easily, very easily. And then you need to post-process it using several techniques so that you can get a good surface finish. There are many researches being conducted in this area. So getting into the FDM or FFF technique, these are the different parameters which can be adjusted in a slicing software. Layer thickness, shell overlap, infill density, its pattern, raster width, infill angle, top and bottom layers, its pattern, printing speeds can be varied, print temperature, build orientation, air gap, nozzle diameter. There are so many process parameters in FDM. Let's see it one by one. I'll be going very fast in this process parameters so as to show you the live demonstration on the slicing software as well. So what are the characteristics that can be studied in a FFF or FDM 3D printed part? So you can study the dimensional accuracy of the part, surface roughness can be studied, mechanical properties or tensile strength, compressive strength, flexural yield strength, impact, elastic performance, hardness can be studied out of the 3D printed part which is obtained from the FFF or FDM technology. Even the build time, lattice structure and build volume can also be researched for different materials available. You can research these characteristics so that you can get a good you can compare the materials which is apt for which application. So there are a lot of researches going on in this area. So moving on to slicing, as Mohammed Bashir said, it's a program which converts 3D digital models into printing instructions, which is called G codes and M codes, which is similar to the CNC method. This slicing software, when inputting it with 3D printing design, it converts the STL file or the digital data into a G code, where we input the G code into the 3D printer to build an object or build the manufacture the final component. There are many slicing softwares which is available. This is one of the popular slicing software, Idea Maker, which prepares 3D models for 3D printing and turns them into G code file for the 3D printer. You can also add custom 3D printers into this software. This is a open source software supported by Race 3D. So we can download the Idea Maker in this link. Hope you have received the link. You can just download it in the link. If you are a Mac user or Windows user, there are many versions available. Even the basic versions are also available in the same link. So next one is I'll just go through all the options available in the slicing software so as you can get a good glimpse of the options available. And then when I'm sharing my screen along with the Idea Maker software, you can view it live regarding the options available. So you can just easily understand when I'm teaching you in live. So first thing is we need to import design file into the slicing software. So you have a plus symbol or you have a import symbol in the slicing software where we can import STL, OBJ and WRML files into the slicing software. we cannot import a SolidWorks file or a Pro-E CATIA file or Autodesk file into the software. You can just import it as a mesh file or STL OBJ it's called. So you can import the STL file into the slicing software, and there are many options which is available in the slicing software. So this is how it looks. You have a plus symbol, and you can just import or you can add new component using this icon. So you just add a STL component, and there are many tools available in the toolbar. So the first one is the add command, where you can add a 3D printing design. There is a delete command. You can view, you can pan, you can move the component, you can rotate the component, you can scale it as per the requirement. You can free cut it. You can cut the components into different pieces using the free cut option. You can just input the amount of height where the cut needs to be done. You can automatically, manually, and automatically give support material to the printing object. You can duplicate the object. You can also repair the STL file. In certain STL files, there will be broken meshes which is available. So when importing, there will be exclamatory symbol available at the right side bottom part. So if the mesh is not perfect, or it's not watertight, or where it is slightly damaged, using the repair option, you can automatically repair the 3D printing STL file so that the output will be good. And there are other options as well. You can connect it online using the connect option. So coming to the basic characteristic of 3D printing in terms of part strength, these are the three important points which is need to be satisfied in every 3D printing method. So first one is the large surface area on the platform. In order to get a good part strength, you need large surface area placed on the platform. And the second one is minimal support should be available in the 3D printed part. And the third one is minimum Z height. So this is a tensile strength specimen according to the ASTM standard. So as you see, it's a FDM 3D printer where the filament is getting loaded, and there are three orientations which is shown here. One is the flat orientation, and the second one is the on edge orientation, and the third one is upright position. So in this, which one follows the 3 points? It should have a large surface area on the platform, minimal support should be there, and minimum Z height should be there. When you see the upright position, the Z height is very high. And in the case of flat orientation, the Z height is very low. And in terms of support, these two things get support material, support structures, because of its overhanging capability. And in the flat side, you don't need any support to 3D print. And in terms of large surface area on the platform, the flatbed orientation is the best technique, where it supports, where it satisfies all the three characteristics to get a good part strength. So when we are placing a component in a 3D printer, you need to take care of the build orientation, in which side we are placing it. So this build orientation depends on various parameters. Like if you are going for a good highly finished component, there are instances where we need to sacrifice the finish of the component, where we need to sacrifice the finish of the component. So we need to choose on which application which we are using. So in case of this VLC player 3D printed model, there are two orientations which is available. If you need a good part strength, you need to go with this thing, because the Z height is minimal, where you can improve the part strength. And if you need a aesthetic look, you need to go with the right one. So these are the two orientations which is possible in this. And there is another possibility. You can just keep this in the upside down position. It is also very similar, so it's not shown here. So it depends on the technology used as well. And if you are using a technology where the support material can be removed easily, or where the support material can be is soluble in water, there this is the best orientation which is possible, so that aesthetic will also be there, as well as the part strength is also there. So after we import the STL files into the slicing software, you can just click on the start button in order to slice the or input the parameters into the slicing software. So it is where we select the printer and the filament used. There are obviously preset parameters which is available in the slicing software. You need to, if you need to adjust it, you just double click on the any one of the template, or you can click on edit in order to edit the parameters. So getting into the parameters, there is the first parameter is like layer height or thickness, or it's also called layer resolution. It's the thickness of each and every single layer. So it is denoted in mm or microns. So this layer height depends on the nozzle diameter. So if you are using a 0.4 mm nozzle diameter, you can achieve a layer height of 75% of the nozzle diameter. If you are using a 0.4 mm nozzle, you can achieve up to 0.32 or 31 mm resolution in the 3D printer. Or if you are using a 1 mm nozzle diameter, you can achieve 0.75 or 0.8 mm layer thickness, so that there will be better adhesion between the layers. So this layer height, layer adhesion, nozzle diameter, and build time and volume also depends on these factors. So if we give a good layer height, like 0.3 layer height, the build time happening is very less. And if we give a lower layer height like 0.2 or 0.1 mm, the time required to 3D print the component is bit high. And the if you are using a bigger nozzle diameter, the volume is also very high. The volume of material used is very high. So as you see in the representation here, so in 0.3 mm layer height thing, the 3 in order to manufacture 3 mm component, number of layers involved is 10. So take one layer takes around 1 second. In 10 seconds, it's over. But in layer height of 0.2 mm, the number of layers is 15, and 15 seconds is taken in order to build the same part. And in case of layer height of 0.1, 30 seconds is required to build this part. So it depends on the number of layers and the layer height, the part time, build time. So this is the first window where you can input the layer height 0.3 mm, which is inputted here. You can also change the first layer height. There are other options as well, which we will be discussing now. Next one is the shell. Shell refers to the thickness of the model's wall. So this shell is the outer perimeter to the 3D printing model. So in this, you can see there are two shells which is available here, and here it is of 5 shells, here it's 10, and here it's 15. You can see the thickness variation in each photo. So increasing the number of shells can increase the part strength, but it can also increase the build time as well. So in case of we are using 2 shells, there is an option called shell overlap, which determines the adhesion or bonding between the shells. So in case of these 2 shells, imagine we are drawing something. You will be giving the outline first and then filling it with the shade. You will shade the fill inside. So it's the 3D printer also works similarly. It first the first shell is being laid and then the second shell is laid. And if you give a shell overlap percentage as 15 or 50%, the first shell will be like this and the second shell will be overlapped according to the percentage which is provided in the slicing software. So it can increase the strength. So after giving the shell in the first tab, you can also vary the infill quantity. The infill density represents the amount of material inside the model. So you can have a completely solid model or a 0% shell model as well. You can also have a surface model as well in a 3D printer. So this is the tab where the infill can be provided. The infill percentage can be provided in the tab, and there are different layer patterns which is available, which is explained in the coming slides. So if you give infill as 10%, the product looks like this. So less amount of material is being used inside, whereas the outer shells are intact, and it's used for prototyping purpose. If it's used for prototyping purpose, we can use up to 50% infill. And if you're using it for a working end product or functional product, you can go for 70% or 100% fill product. So changing the infill density also increases the time taken as to 3D print the component. So these are the different patterns which is available in the 3D printing sizing software. One is the grid, rectilinear, honeycomb, triangle, cubic, concentric, gyroid, lines. So these are the different 8 types of infill pattern which is available. So based on the application, we can change the infill pattern types. If you need a good strong part, you can go for gyroid or honeycomb structure so that you can get a good part strength. So this picture depicts the different build orientations which can be kept and how the layer thickness influences the layer adhesion. So this is the brown one is the first layer and the blue one is the second layer, where it imprints onto the first layer, it adheses over the first layer. So there is a good bonding between layers happening. And this is a 3D printed cross section of a part. So the outside shells is called contours. Its other name is called contour shell or contour. So and for infill, the other word is called raster. So you can also vary the infill angle and the infill width as well. So there are instances where we can control the air gap as well. So next is the platform addition, where I said there is an effect called warping effect happening in 3D print, where the 3D print bends in an upright manner. In order to reduce the warping effect, there are different platform additions available. One is the raft, brim, and skirt options. So this is the tab where the raft, brim, and skirt can be added. So this is called the raft, and the raft line type can also be varied. Lines, rectilinear, everything is available. In order, if raft is given, this is something like a raft. Hope it's visible. So the 3D printed component can be separated right away from the raft, so that there is no warping effect occurring in the 3D printed component. So this is a temporary base which is being printed first, and then the 3D printed component prints over the raft in order to minimize the warping effect. Or if you are printing a small cross-section component, you can use raft in order to avoid the toppling of 3D prints. The next one is the skirt. In order to get a neat 3D printed component, there will be material deposited outside of the 3D printed model, so that it ensures that enough material is given inside the 3D printing component. So this just happens in the first layer of the 3D printing. So BRIM is something like it's an extra support to the raft or the 3D printing component. It consists of different lines where it controls the or it presses onto the 3D printing component so that warping can be minimized. And the print and bed temperature can also be varied as well in a slicing software. Different material has different print and bed temperatures. So in terms of temperature, there are two kinds of errors which can happen. One is the under extrusion, the other one is the over extrusion. As the name represents, this is called under extrusion and this is called over extrusion. If the temperature of the 3D printing material exceeds the melting point or the exact temperature of the filament, over extrusion can happen. So this will be in a rugged manner. It will not be a good surface finished component. Whereas if the 3D printing nozzle doesn't attain the melting point of the filament, under extrusion can happen where improper layer adhesion also happens. So we need to find the exact 3D printing temperature in order to get a normal 3D printed component. So in under extrusion, as the nozzle deposits the material, improper extrusion is happening because it hasn't reached the melting point of the material. So improper extrusion happens and layer adhesion is getting reduced, as well as there will be gaps in the 3D printed component, so that the finish with the part will not be good finished. And in case of normal or optimal extrusion, the extrusion is very perfect, the layer adhesion is good, and there are no gaps involved in the 3D printing component. In case of over extrusion, if we overheat something, there will be bubbles which is forming, or it can expand. So in this case as well, the material flows too much outside the nozzle, so that the layer adhesion will be good, but the layer finish will be very minimal as possible. So these are the different materials which is used in a FDM 3D printer: PLA, PETG, nylon, ABS, ASA, PC, Ultem materials. So each one has a different glass transition temperature and melting temperature. So in case of PLA, the print temperature is around 205 degrees. And in case of ABS, it's around 240 degrees. And we need bed temperature for almost all the materials. In case of PLA, there is no bed temperature required. But in some materials, there is a possibility of giving a bed temperature. And each material has its own printing characteristic. Some are easily printable and some are difficult to print. When comparing PLA with ABS material, ABS is a bit difficult to print, and there will be a full order which is coming out when printing ABS. So we'll be using good exhaust techniques, and we should be printing it in an enclosed chamber so as to get a good surface finished 3D print component out of a ABS material 3D printer. So as I said, the other 3D printing parameters is called the top and bottom layer infill angle. So we discussed about the shell and the infill nature of the 3D printing component. There is something called top and bottom layer infill, where if we are giving 10% infill to a component, the shells are formed and less material is getting deposited into the 3D printing component, whereas the bottom and top layers should not be left open. So we need to solid fill the top and bottom layers, and this can also be controlled using the slicing software, where you can provide the number of top and bottom layers which is required for the printing component. So this also has the different pattern types which is available. Lines, rectilinear and concentric line pattern type is available for this top and bottom layer patterns. Print speed can also be varied in the slicing software, where optimum print speed is 80 mm per second or 60 mm per second. It depends on the material which is being used. PLA can print up to 100 mm per second. ABS can be printed in 80 or 60 mm per second, whereas PETG and other flexible materials should be uh, fed in a rate of 50 or 30 mm per second so as to get a good surface finished component. So these are the nozzles which we are discussing. It is of different types. We use two kinds of FDM 3D printer. One is FDM 3D printer which uses 3 mm raw material. 3 mm is the diameter of the raw material used, and the other one is the 1.75 mm raw material 3D printer. So in 1.75 mm raw material 3D printer, the different nozzle sizes available is 0.2 to 1 mm nozzle size can be availed in a 1.75 mm 3D printer. And there are different materials which is also used: brass, steel, hardened steel nozzle, Osborne ruby laser, ruby nozzle can also be used. These different kinds of material is used to handle different kinds of printing materials. If you use a carbon fiber filled thermoplastic, you need to use a hardened steel nozzle so as to reduce the wear of the printing nozzle. So if you are using a brass material for a carbon fiber filament, if we are using, say, for example, if we are using a 0.4 mm brass nozzle, once we start use the carbon fiber filament, after a few prints or 2 days of time, the nozzle gets weared and it gets converted into 1 mm nozzle. So there is a lot of wear happening in a brass 3D printer nozzle. So this nozzle, by changing the nozzle, you can also achieve, you can vary the layer height as well, and also the time taken is also depends on the nozzle size. In this case, when using 0.25 mm nozzle, this is printed in 3 hours. Whereas the same thing when printed with a 0.4 mm nozzle with a good extended height, you can print the same thing in 3 hours. And in case of 0.6 mm nozzle, you can print a larger structure than the 0.4 mm nozzle in the same 3 hours. So the time taken reduces as we change the nozzle for a single same component, and we can, it's all dependent on the nozzle size and the application where it is used. So this is the fishbone diagram in order to offer the different process parameters available. In order to, if you are going for opting for a research, you can just follow the fishbone diagram, which is depicted here. It's taken from this research paper. So in order to analyze the tensile strength, you can vary these things so that you can get the comparison of on the tensile strength between different materials. So this is something which will be very helpful for researchers who is doing research in 3D printing technology. So the next thing is you have inputted all the process parameters. Just click on slice button. The product is getting sliced, and then the output can be taken out of the slicing software. You can export the G code out of the slicing software. You can also preview the number of layers which is available, and you can find, you can just simulate the component so that you can find some, if there are some errors in the component. So this is how a preview looks like. It also depicts the filament amount used, or you can also estimate the amount of filament used or weight which is used, the length of filament used. Everything can be is shown in the slicing software itself. The time taken is also shown in the slicing software. As you can see, it tells us the G code which we are sliced. and the estimated print time is also depicted here, and the amount of material used and the estimated price as per the information given by us can be seen here in the window. So this is a presentation of a G-code file exported out of the slicing software. So this G-code file is being inputted into the 3D printer so as to start the manufacturing process. So I'll suggest a few researchers which will be a good input to the session. You can compare different composite 3D printing materials. Different filaments can be processed, and it can be compared based on the application which you are using. You can also compare a post-processed materials. There is something called salt method, acetone vapor treated, or epoxy coated method, where you can compare using these post-processing materials. So I'll share my screen and show you the representation of the IdeaMaker software. Hope it's visible to you. So this is how IdeaMaker software looks like. You can just start with import models. I'll go with tensile specimen. This is how a tensile specimen looks like. You can pan it, right click, and you can rotate using the mouse to view it in all directions. You can just click on the home button to return to the home position. You can move the component in the build platform. You can click on on platform to place the component onto the platform. You can use make center to move the product into the center. And if you have multiple materials, just use Control C and Control V for copy pasting of materials. And press Control A to select all the materials. You can just click on arrange all models so that it will be automatically arranging the specimens accordingly to the as per the IdeaMaker algorithm. So we are going to just slice a single component. So you can also scale, rotate the build. You can change the build duration using the rotate command. See, using the arrow marks available here, you can just transform or rotate the component in the preferred build orientation. This is the on edge build orientation. This is the flat orientation, and this is the upright type build orientation. If you need to scale the 3D printed component, you can change the percentage scale here. You can also cut the specimen into two parts using the cutting plane in the free cut option. You can move and you can change the values of Z as well in the cutting plane software. So you can also add support structures to the model. So since the overhang angle is high, we can reduce it. So sorry. So when putting for a 45-degree angle support structure, we will just put the overhang angle is 45 degree and the pillar size is 1 mm. Just click on create auto supports. You can see supports generated below the 3D printing component. And in some cases, this area will be in a yellow exclamatory mark, which means the mesh is not intact. So in that case, you can just click on repair option and click on auto repair so that it turns to green. Only then the 3D printing design is perfect. So these are the basic tools available in the toolbar. And let's see how we are going to slice. Click on start slicing. You can just edit the options using double clicking it. You can see different tabs available. I've taught you like you can change the layer height of the component First layer height can be varied, shells can be varied, shell overlap percentage can be varied, and there are a lot of other options as well, which is not required for now. You can change the infill percentage. You can change it as, I will give it as 25%. The infill overlap is 15%. And the infill pattern type, I will give it as honeycomb structure. Then the top and bottom top and bottom layers can be changed. I will give it as I will give it as 5 bottom layers and 3 top layers. And then support materials parameters can also be varied under the support tab. Platform, in case of platform additions, you can just give raft with skirt to the component. Since it has a reduced cross section, it has a high possibility of getting toppled out of the 3D printing platform. So I'm giving raft with skirt as the platform addition, and the surface area is also very high. So there can be happening of warping effect. So I will be giving raft with skirt. And then using the cooling option, you can adjust the fan speed of the 3D printer. You can adjust the temperature of the bed and the nozzle using the temperature option in here. And then you can also alter the speed accordingly using according to the material which is being used using the speed option. And there are other options as well, which is very much not required for now, and only advanced users will be going with the other options. So there are a few things which can be done. If we need to change the color at the middle of the print, you need to just add a pause point in the 3D print. So if I'm giving 1 mm as the pause point, you can just click height is given as 1, add pause point. So it is detailed as 1 mm at 1 mm after the printing is when the printing is done. After reaching 1 mm, the printer pauses and the head moves out of the way, and you can change the raw material to another color. So 2 different colors can be obtained using the pause option. You can click and remove the same pause point as well. You can just save it and slice. You can see the windows, like you can view the product's name, G code, tensile G code, and the estimated print time is around 1 hour 16 minutes 48 seconds. The estimated amount of material used is around 17 grams, 5.59 meters. And let's see the preview simulation of the 3D printed component. This is how the 3D printed part looks like. So I'll just zoom in. This purple one is the skirt, the yellow one is the raft. This is the build part which is printed, and the blue one is the support structures. So as you see, there are different layers which is visible. You can just use this tab in order to view the inside of the model. As I said, I have given 5 layers in the bottom. I'll show you how the 5 bottom layers happen. First layer, second, third, fourth, fifth, and then the infill starts. It gets 3D printed, and in the top, it is of 3 top layers. So once it reaches the top, 1, 2, 3. There are 3 top layers which is visible. So the whole 3D printed part is printed in 25%, which is a good infill ratio. By increasing the infill ratio, by increasing the amount of material used inside, the time will vary accordingly, and the weight of the product will also vary according to the infill which is used. So this is the representation or a demonstration of the IdeaMaker software. Hope you enjoyed the session. I've told maximum parameters in the short span. Hope you understood all the parameters. So any doubts, you're free to ask.
Thank you, sir.
Thank you, sir.
Thank you, sir. It is enlightening on all all the softwares you have shown. It is amazing, sir. We are
Yeah.
new to that software.
Okay. Yeah.
Yes, sir. Any questions, participants?
Hello, am I audible?
Yes, sir.
Yes, sir.
Hello, nice presentation, Joseph.
Thank you. Yeah.
It is the software you have used. It is available on net. It is free downloadable. But
Yes.
let me know whether if you are purchasing some machine, say let us say Stratasys or maybe any other brand, they have their inbuilt software.
Yes.
What is the difference between the freeware software slicing and the particular company made slicing software?
Yeah, so few companies like Stratasys 3D Systems, they prefer their own softwares because
Right.
it's kind of closed loop, it's their business, and they'll be obviously closing it. They'll be telling that you should slice with the softwares prescribed by the Stratasys of 3D Systems. Only then the output also depends on the slicing software. If you're using some third-party software, you can't get a good output. It's a free version of software which is available in the internet. If you're going for a paid version of slicing software such like Simplify 3D, you can get a good amount of different other process parameters as well. So it depends on the machines which we are using. So this software is not compatible with Stratasys or 3D Systems 3D printer.
Right. Okay.
Yes.
And what is the difference between the particular, say, company, the branded company's parts? Because there is a company called as Ultimaker. Here, the particular printer has topmost accuracy and
Yes.
reliability. Okay, so I seen and I have seen the Ultimaker is the best. Now,
Yeah.
what about the Insta3D? I have not used it at all. But
Okay.
what is your opinion related
So
to this?
we have given 3D printers within Coimbatore and Kerala.
Right.
So it's almost same. Like Ultimaker is a commercial version of the FDM 3D printer. So these commercial 3D printers are called it's almost a kit version 3D printer, which is being built in every new 3D printers. It's like it uses stepper motor, printer controllers are available, and basic structure is the same. Just the casing differs.
Right.
So the representation of the product is differing in. It's the basic difference seen in the new printers. The
Again,
technology and the features is the same.
right, sir. And last question:
Yes.
did you have any material, say, rights? Because Ultimaker for Ultimaker printer, we have to use predefined material, which is to
Yes.
be sold by the particular company only. Okay.
Okay.
Or in other word, I can say Ultimaker provides some material along with the printer. So
Yes.
that has to be used over a long period of time. You
Yes.
cannot try with a local material having the same dimension.
Yeah.
Or you cannot get guarantee that this will be printed correctly.
Yes.
So
So it is.
likewise, you have that say monopoly of the material and the thing.
No, we don't go with monopoly of the material. You can use any third-party filaments sold in the market. Only that the material which is used should be of tight tolerance. If it is 1.75 mm filament, it should be playing around 1.73 to 76 or 77 mm. So only then it's the basic characteristic of the filament. If it has a good tight tolerance into it, everything is printable. And
Right.
you need to change the process parameters according to the filament which you are using. It also differs between colors as well. The same manufacturer, red color will be in a different print temperature, white color will be in a different print temperature. So we need to analyze
Right.
these things. Only then you can get a good surface finish or good
Right.
print.
Thank you. Thank you very much.
Thank you.
So thank you, sir. I thank you for your enlightening speech and enthusiastic participation. I thank Mount Basi sir also for this presentation. Once again, I thank you so much, sir. Thank you, sir.
Thank you, sir. Thank you.
So the next session will start at 2:15 p.m. in the same link. Thank you.
Thank you.
Thank you so much. Close the video, sir. Hello, Joseph, sir. Hello. Hello. Hello, sir. Hello.